This next question in Chapter 4 is asking how much the chemical potential of copper is changing when, so it's a pure substance, when the pressure exerted on the copper goes from 100 kilopascals to 10 megapascals. And so what the question is really asking for, but doesn't explicitly tell you, is d mu by dp at constant temperature is what for a pure substance? We know that the chemical potential of a pure substance is the same as its molar Gibbs free energy. And we spent a lot of time trying to find out these sorts of rates in terms of easily measured properties or easily looked up properties. And this one we would determine, okay, and we may need to show how we determine that. We would start with G. G is equal to H minus TS, and therefore dG is equal to, and we would do that. We would derive that equation for dG, and it is in terms of two properties. Then we would divide it through by dP at constant temperature. And we have plenty of examples of these earlier on in the course. And when we do that, we would determine that the solution to it, the expression, really dissolves down to one easily measured property, and that is the molar volume of copper. So I say easily measured or easily looked up. So while I don't typically have the molar volume of copper listed in a table to look up, I do know its density. And so I find that dG by dP, or d mu by dP, constant temperature, is equal to the molar volume. So I split that up. Excuse me. So I take off the brackets and I bring that up. So I get dG is equal to dpVm, or vm dP. Sorry. And then integrate the whole thing, and I have delta G being equal to the molar volume times delta P. And what I've done in that integration is to assume that the molar volume over that temperature range is staying constant because it's of the solid. What that also implies is that the density of the solid is not changing. But in the range of sig figs that we have, it's safe that it isn't. This is a scribble, I'm sorry. And this is just to show you, and I also apologize for the quality of this camera, but I'm not in the office at the moment, and this is as good as it gets. Units of molar volume are milliliters per mole, or if you like, centimeter cube per mole. Now, note that if I had a molar mass, grams per mole, I do know it's copper, so I have a molar mass, divided by the density, or multiplied by 1 over the density, that would actually give me units of volume per mole, which is a molar volume. So this becomes molar mass divided by density, slipped back into this same equation. Now remember, the delta P is given, so let me slide this up. I've decided not to recopy this in a neat form for you because I think you can just follow along with my first draft. Delta G is equal to my molar mass for copper, 63.546 grams per mole, divided by density, or multiplied by 1 over density, so 1 cubic centimeter, 8.96 grams. That's the density of solid copper. And the change in pressure was 10 megapascal, so 10 times 10 to the 6, minus 100 kilopascals, 100 times 10 to the 3, so there's Pascal. And I know I have to dig into the SI units here for this to make sense and ultimately be equal to joules. So right away I'll say that a Pascal is a kilogram per meter per second squared, And then I continue this over here, because my Pascal will go out, and then I'm left with a bunch of SI units, so which I probably want to convert to joules, so I multiply by 1 joule is a kilogram meter squared per second squared. And then I noticed that I still had cubic centimeters, and I needed to bring that to cubic meters for things to cancel. So inside the bracket I said that 1 meter is 100 centimeters, so then I cube both the top and the bottom. And so in my calculation I did 10 times 10 to the 6 minus 100 times 10 cubed, and then I divided by 100 cubed, multiplied by 63.546, divided by 8.96. And that's the number that I got, and then I took down all these units to make sure that they were correct. So I went through and collected all the units on a general sort of numerator and denominator, and I ended up with joule per mole as outstanding, so that's perfect. And the answer is, I don't know if you can tell, that's 70.212, 656. I just copied down all the numbers. Yeah, and it's positive, so that's the answer is 70 joules per mole. It's a really good question. It's a really good question, and you need to be prepared to show that dG by dP at constant temperature is equal to the molar volume, and you need to be prepared to define molar volume in terms of molar mass and density. That will not be pointed out to you in a test, midterm, midterm or exam. So you have to be sharp on that. The SI units for a Pascal and a joule are always given, but they're not going to be given in the question, so it's not like you're going to have a flag to this conversion, right? But those SI units for Pascal and joule are given in a general data sheet. Okay, so enough on that. It's a really good question.